quickly realize that vectors are not straight things. AB is to the positive x, whereas DC is to the positive is to the negative x axis. So similarly, when we are summing up, when we are given the magnitude, now in this case, the magnitude of AB is 30, whereas the magnitude of CD is negative 30. So when you sum up AB and CD, the value is equal to 0. Okay, so assuming that AB and CD were acting on a given body at the point between if a point, and then you put a vector AB pulling the positive x in towards, but by calculation equal to 0. What does this mean? Can someone send me a message and tell me what that means if we really understood the concept of static equilibrium? I'm giving a chance to the first two. We have seen from that example that AB plus CD, where AB is equal to 30 positive and CD is equal to negative 30, when we sum them up, it is equal to 0. And I'm saying, assuming an imaginary body between D and A is being stretched on one side by AB and on the other side by CD, what will happen? Realistically, because now that is when the engineering, relating to the engineering problems comes into play. And guys, question of Grace and Joab, their answering is the same, but it is just an issue of the language. Question of Grace says the body will not move, whereas Joab says the body will remain constant. Okay? Instantly, since forces are equal. Exactly. Now, that if you, it is an extra, and that body has got an internal force that can resist this force. There is no damage, there is no deformation, there is no deflection, there is no displacement that will occur. Let's say, yeah, if I used this small cup of mine, if I use this small cup, now this is what we are talking about. When I tend to push this cup, you see, when I push it slightly, you see, I'm actually touching it. You can't realize I'm pushing it. Why? Because the force I am subjecting on the cup is not sufficient enough for my hand. So if my finger is slightly pushes the cup, reason because its resisting ability is less than applied force. Okay? Now, So I can see my time is warning, but basically that is what we will be dealing with. So in the methods of in the methods you're supposed to look at under vectors, we are supposed to look at vector addition. One by graphical method, and the other graphical method, that is where we'll discuss things to do with triangle forces, which is this one. If you have a force AB and a force DC, what is the resultant? The two vectors. So the resultant of vector AB and DC in this case is the vector AC. It is simply the resultant. Okay? Kind of time elapsing that. And then the other thing which we'll be looking at is the issue of the triangle forces. But before we go for triangle forces, we will also look at the parallelogram law of addition of vectors. It simply means that this vector V1, this vector V2, if we draw parallel lines at the edge here, you can actually try this at home, and you say maybe V1 is equal to 10. Please take it as a trial at home. If V1 is 10 and V2 is, let's say, 8. Try to draw a parallelogram simply means that this line is equal to V1 but parallel to V1. They will never meet. So whichever angle you choose, for uniformity, let's take the angle between V2 and V1 as that is V1 between V1 and V2. So lots of also has to be 45. Which from this point, this one, so V2 with this line, so this one. So that is all about the graphical method. But mainly, its limitation is it usually works for not more than 2 forces. So when the forces are more than 2, then we will go for method that we call method of solution, resolving the components in terms of x, y. When we have more than 2, then the triangle forces in the parallelogram method cannot help us to get the result. And so we go for method which we call the component method of resolving both. So in terms of the x and y components, which is usually this, okay? Where you have this is the force acting at an angle B, then we will get the component of A in terms of x, then in terms of, you remember this rule, which one falls in which. This example using graphical method. Prior to this example, we are saying the car drives at 6 kilometers, so that this x is the unit. Is simply a straight line. Yes, method of resolution, I will do an example. Here I cannot, I just wanted to introduce you. Okay. But someone is saying, sir, can you do an example? So I'll do that. But for this example, kindly do it as a take-home using the graphical method. Using the graphical, it is as simple as drawing a line of 36 as the unit. This is a straight line from 0, 0 towards east. Then drives 45 kilometers north. From wherever this point stops, you draw another line towards the north. Then it drives 25 kilometers northeast. You look for northeast using this canvas and protractor, whichever is easier for you. And then after that, you would match the point from where the car started and the point where the car stops. That is the graphical method. Then it tells us What is the result? And that will be the resultant force. If I exclude the zeros, come and do, I will send you what you know, forces. Okay? When I say that, you go ahead and do. Otherwise, thank you. I believe you know. Put it as feedback. Someone says the body will remain constant. Thank you so much. Let's stay still. This is very correct. Jalab Robert says the object will remain static since forces are equal. In simple terms, the body is in equilibrium, static equilibrium along the x-axis. And then Galima Jonam says, so you should give us a worked example showing the y values and x values within the components. I will do that, Jonam. Kindly remind me within the week. Amanya says, thank you to sir. Thank you so much, guys. Have a blessed week. Let us have a group only for engineering mechanics so that in that group I can always share whichever information you need. That's when I don't have time. A lot of time for students. Otherwise, thank you so much. Let's meet again next week. I promise to try have the Zoom app and the PC working so that I can always share with you the screen to make it very, very easy. Thanks. Have a blessed week.